What if our civilization was not the first to shape the earth? Imagine a quiet layer of stone that remembers a vanished age, while every monument has turned to dust. We stand at the surface with short memories, while the planet keeps its own long account. The only fair way to ask this question is to look for marks nature rarely makes at a global scale. If those marks exist, they will be faint, but they will be real. We are used to thinking that intelligence bloomed once, that our tools and stories mark a first moment. We measure pyramids, temples, and old foundations, then draw a clean line toward today. Yet this clean line may be only the last chapter in a very long book. The surface of the planet changes and erases with patient force over vast time. What would remain of any society after many millions of years? The continents drift, the oceans rise and fall, and climates swing over spans beyond ordinary imagination. Over 4.5 billion years, rock has been made and unmade, and entire mountain chains have been leveled. Plate motion drags the crust into the deep mantle, where stones and cities alike would be recycled. Wind, water, and chemical weathering strip away the proud markers of a short age. Against that background, silence is not proof of absence. So the absence of monuments is expected, not decisive. This is why some researchers propose a careful thought experiment sometimes called the Silurian Hypothesis. The name recalls an old story about intelligent reptiles, but the idea is not about monsters. It is a sober test. If an industrial society had risen long before us, what global traces could survive to the present? Direct artifacts would almost certainly be gone, so the clues must be subtle. Here is the promise. We will test patterns, not legends. We would need to search for fingerprints that nature itself struggles to make. Streets, glass towers, and bridges would not last across deep time. Wood rots, metals corrode, and concrete cracks and returns to sand. Even plastics, which feel stubborn today, break down under light, heat, and pressure. Ordinary objects are not designed for spans beyond many lifetimes, let alone for millions of years. If a society faded long ago, its common goods would dissolve into the geology. So we must look past shards to the chemistry that endures. So the search must turn from objects to signals. Rocks, ice, and deep mud carry a continuous record of the planet's chemistry. Layers capture what fell from air and water across long intervals, like pages in a slow diary. The goal is to find patterns that look unnatural at a global scale. If the patterns do not match volcanic pulses, asteroid strikes, or natural carbon shifts, then the signal is interesting. This turns a dramatic idea into a measurable task. One place to look is the carbon cycle, which links air, water, life, and rock. Combustion of buried carbon drives clear chemical signatures in the atmosphere and oceans. When a great deal of buried carbon is burned in a short time, certain isotope ratios swing in a specific direction. Nature can do this through massive volcanism or rapid warming events, and we can measure those episodes in cores. The challenge is to separate a potential industrial pattern from natural extremes with similar shapes. It may sound like science fiction, not Star Trek, but stratigraphy. If a past society used large amounts of fossil carbon, the sediment layers might show a sharp global carbon isotope excursion. The shift would align with warming, ocean chemistry changes, and altered rainfall. we would expect a pulse that rises quickly, then decays over centuries, to millennia, as natural buffers recover. The exact profile matters because some natural events are slower or leave different side effects. Careful comparison is the only honest way to test the idea without overreach. Another search path focuses on synthetic materials and their breakdown products. Plastics do not remain whole across millions of years, but their tiny fragments can be trapped in sediments. Additives and pigments can linger, bound to clays or preserved in cold, low-oxygen mud. Polymer chains may break, yet distinctive compounds can still persist as altered residues. If such residues appear in the same age layer across distant seas, the pattern deserves attention. That would be a small reward for patient listening. Metals also offer clues because industry concentrates and moves them at unusual scales. Mining and smelting release characteristic blends into air and water, which then settle into sediments. Ratios of certain trace elements can look odd when compared to the usual crustal mix. You would expect unusual enrichments near population centers and river mouths, then a global dusting over time. A sudden worldwide change in these ratios could signal activity beyond the usual geological drivers. If that step aligned worldwide, curiosity would feel earned. There is also the matter of radionuclides, produced by reactors and other high-energy systems. Many man-made isotopes decay quickly on geological scales, which makes them poor long-term markers. Yet some decay chains alter nearby element ratios in minerals, and some isotopic imprints can endure. If those imprints appeared in a single thin layer worldwide, they would be hard to confuse with nature. The absence of long-lived artifacts pushes us toward these faint, durable chemical hints. Finding such an imprint would be sobering, not sensational. Fossils of bodies or buildings are not reliable guides at these scales. The fossil record is sparse even for hardy shells and bones, and soft materials vanish first. Most ancient land surfaces are gone, ground into grains or swallowed by the mantle. Even long-lasting stone blocks erode and tumble, losing form long before the next age arrives. Expecting a statue or wall to greet us after tens of millions of years is not realistic. The oceans, however, keep a steadier archive. Fine particles drift down and settle into thin annual layers, especially in calm basins with low oxygen water. Those layers trap chemical information about the sky and the continents above. Drilling ships can pull narrow cylinders of this mud and read the sequence like a long timeline. If any global industrial pulse happened, a whisper of it should be pressed into those pages. If a whisper repeats across oceans, the pulse becomes hard to ignore. There is a limit to this archive because the seafloor is not eternal. New crust forms at ridges, and old crust sinks back into the mantle along deep trenches. This process, called subduction, recycles the archive over spans of 100 to 200 million years. That means the very old ocean floors are gone, along with any signals older than that range. The window for discovery is wide on human terms, yet narrow against the age of life. Even that window, if used well, can speak volumes. On land, lakes and swamps sometimes preserve rich sequences, especially where new sediments bury the old quickly. Peat bogs and river deltas can hold chemistry for long ages if disturbance stays low. Desert basins can trap dust and ash in thick stacks, that last longer than surrounding hills. Caves can grow layers drop by drop that encode subtle changes in water and air. Each setting has biases, but together they offer diverse shelves for the past. Together, they offer patient proof or patient refusal. When searching these shelves, the order of events matters as much as the signals themselves. First, seek a rapid carbon shift that points to large-scale combustion. Next, test for parallel changes in temperature markers, ocean acidity, and sedimentation rates. Then, scan for trace element ratios and synthetic residues that align with the same short window. Finally, ask whether known natural processes can account for the full pattern without stretching plausibility. This scaffold keeps curiosity from drifting into wishful thinking. Clarity comes when many small hints point the same way. Skepticism is not an obstacle here. It is the method. Any extraordinary suggestion must be weighed against ordinary engines like volcanoes, methane releases, or impacts. Only when natural explanations fall short should an industrial cause be considered as a working idea. This protects the inquiry from turning into a story that flatters human uniqueness or fear. It also respects the complexity of a planet that has surprised us many times. Doubt, handled well, is a form of care. It is natural to ask why this line of thought matters if the result is likely negative. The value lies in learning how civilization appears to geology at all. By building a clear list of expected signals, we sharpen our tools to read the past and the present. We also frame our own layer in a way future readers could test, if any exist. The practice turns a grand question into specific measurements. That alone is worth the work. Consider the record of previous rapid warming events that occurred long before our age. They show how carbon shifts ripple through climate, oceans, and life, sometimes with sharp extinctions. These episodes teach us what a natural pulse looks like and how long recovery can take. By comparison, a human-driven pulse would have its own timing and byproducts. The contrast helps prevent false positives and gives the search a disciplined path. Contrast prevents us from fooling ourselves. We should also reflect on what kinds of beings might have made such a mark. If any did, they may not have looked like us or built with our favored materials. Their economy could have focused on resources that leave little obvious trace after long spans. Their settlements might have been coastal, which makes them vulnerable to sea level rise and storm erosion. If so, many direct remains would fall into the sea and join the quiet archive there. Machine remains are not likely to survive, yet energy footprints might. Large energy use often leaves waste heat and chemical byproducts that spread widely. Those byproducts interact with air and water, then settle into the sediments we can read. Over time, the molecules change, but the ratios and structures can still point back to their origin. This is why chemistry matters more than broken tools for a search across deep time. Energy leaves footprints even when machines do not. If we are honest about the difficulty, we accept that most traces would be muted and mixed. Signals would stretch and smear across layers as mud compacts and minerals grow. Later events could overprint earlier patterns, making clean separation hard. That is normal for geology, and it does not render the work hopeless. It only means the case must rest on several lines of evidence that converge. Convergence is the compass. We also need to accept the possibility that we will find nothing conclusive. A null result would still teach us how fragile complex societies are when measured against planetary change. It would also remind us that many stories feel missing simply because time is a stern editor. This humility keeps the investigation grounded and worth doing. It turns a grand speculation into a careful reading of stone and sea. In this spirit, think of deep cores as a library written in slow script. Each centimeter may cover many years, and each shift in color or grain marks a change above. Instruments can read isotopes, organic fragments, and trace metals at fine resolution. Matched cores from distant oceans can reveal what was local and what was global. A shared anomaly across far basins would be a strong candidate for closer study. Shared patterns across distance are the bright flags. Rivers deliver many of the clues we seek because they sum up the lives of continents. Industrial runoff, soil loss, and combustion residues all ride the same paths to the sea. River deltas build layer upon layer, often with preserved plant fragments that lock in atmospheric signals. If an unusual pulse passed through a continent, the delta would likely catch it. That is why these places are prime targets for careful sampling. Where rivers write quickly, we can read clearly. Ice also keeps a fine record for shorter spans that still stretch beyond recorded history. Trapped bubbles can tell us about past air, and dust layers trace storms and fires. Chemical fingerprints in ice align with those in sediments, creating cross-checks that add confidence. Though ice does not reach back as far as the oldest rocks, it teaches us how signals combine. These lessons inform how we interpret older, more compressed archives in stone and mud. Ice teaches us how signals braid together. Some will worry that such questions invite fear or fantasy. The right response is agency and method, not anxiety. We pose a clear test, we gather data, and we compare patterns with known natural drivers. If nothing remains but natural causes, the work has still refined our understanding. If something odd persists after fair testing, we note it without rushing to grand conclusions. Calm method is the antidote to noise. In the end, the search is a mirror. Learning what to look for in ancient layers teaches us what our own layer will broadcast. It shows which of our actions echo across centuries and which fade quickly. It also shows how resilient the planet's systems are and where they strain. That knowledge is useful regardless of what the past holds. The shape of a global signal matters as much as its size. A brief surge that rises within a few centuries and relaxes over a few thousand years suggests a rapid forcing. Slower climbs, with long plateaus, can point to mantle processes or long-lived outgassing. We read not only what changed, but how quickly and in what sequence. That timing is one of the best ways to separate engines that look similar at first glance. Timing, more than drama, tells the tale. Attribution also depends on bundles of evidence that travel together. A carbon shift paired with soot and specific aromatic residues means widespread burning of organic matter. If the same window shows altered rainfall, faster weathering on land, and ocean chemistry drift, the case grows clearer. Nature can make any one of those patterns alone through familiar events. The unlikely part is a full bundle that moves in lockstep around the world. Bundles, not single spikes, carry weight. Trace metals can strengthen or weaken a case depending on their context. Lead and copper often rise with mining and smelting, while chromium or nickel can ride natural dust from certain rocks. Ratios between these elements can hint at source, because ore bodies do not match the average crust. Shoreline mud near large rivers should show the strongest early response, followed by a thinner global veil. A sudden worldwide step in these ratios across many basins would be noteworthy. When ratios step together, we listen. Mercury deserves special caution because volcanoes release it in large amounts. If mercury spikes sit alone, they are more likely linked to eruptions or mantle plumes. The signal becomes interesting when mercury spikes pair with markers of combustion that point to burned fossil carbon. Even then, we must check for nearby flood basalts that mimic many industrial patterns. Care is better than speed when two causes create similar shapes in the data. Patience beats speed when causes overlap. Synthetic residues offer a different angle because they are engineered, not common in nature. Some fluorinated compounds resist decay and can bind to sediments even after long journeys. Certain chlorinated byproducts are also stubborn and can persist as simplified fragments. These do change with time, yet their simplified forms can still look odd compared with biogenic molecules. Finding the same unusual suite across far oceans would merit a slow and careful audit. Design leaves signatures nature rarely imitates. The best archives for such delicate clues are calm, low-oxygen basins where scavengers and burrowing are rare. In these places, annual layers can stack with little mixing, which protects fine chemical structure. Inland lakes that freeze part of each year can show similar banding useful for shorter spans. Salt marshes and mangrove peats preserve organic markers tied to air and river chemistry. Each site filters the world differently, so a network of diverse sites builds confidence. Diversity of sites builds trust. Biological remains add context because organisms react quickly to climate and chemistry. Tiny shelled plankton adjust which species dominate when waters warm or turn more acidic. Pollen records shift as plant communities move with temperature and rainfall belts. Sudden changes in these living indicators at the same time as a chemical pulse suggest a common driver. When the biological and chemical clocks strike together, we pay attention. Life is a sensitive meter for change. Good timelines depend on clear anchors in the layers. Volcanic ash beds can be matched across continents and serve as sharp timestamps. Shifts in magnetic minerals can also provide broad markers that repeat in a known pattern. Where these anchors are missing, dating relies on steady accumulation rates checked against local events. Multiple methods reduce drift and help align distant cores to the same story. Anchors keep distant stories aligned. Land records bring their own strengths. Ancient soils trap metals and organic fragments, and desert loess preserves long chains of dust that cross continents. Caves grow carbonate layers, drop by drop, that carry signals of rain and temperature. River terraces can pin down when flows rose or fell during a broader pulse. Together these records complement the oceans and help separate local noise from shared change. Any long search must guard against modern contamination. Cores are handled with clean tools, and labs run blanks to catch stray molecules. Dating samples are taken from the untouched center of a core, far from the surface. Teams repeat key tests at independent sites to rule out lab artifacts. The goal is not to be quick, but to be sure. Clean work earns clean answers, Quantitative modeling sets thresholds for what would be visible after deep time. We ask how much fossil carbon must be burned, over how many years, for a clear isotope shift to remain. We ask what mass of polymers or metals would need to enter oceans for residues to persist. These models guide fieldwork toward the narrow windows where a faint signal can rise above background. They also prevent overconfidence by showing when a hoped-for pattern would fall below detection. Models set the stage, and rocks decide. Natural engines provide the best counter-tests. Large eruptions release carbon and dust, but they often lay thick ash and distinct mineral suites. Asteroid strikes leave shocked minerals and rare metal patterns that do not match industry. Methane bursts from seafloor hydrates push carbon ratios fast, yet lack the synthetic residue bundle. By rehearsing these natural scenarios first, we reduce our bias toward the answer we find interesting. First, learn nature's voice, then check for a chorus. Simplicity helps in wording and in method. We state what a layer shows, we compare it with known causes, and we rank the fits. We avoid grand inferences when several ordinary processes can explain the curve. We keep each claim small and label it as a measurement, an interpretation, or a working idea. This steady discipline keeps the inquiry useful even when it ends with uncertainty. Small claims stack into sturdy knowledge. There is also a lesson about resilience. Some systems rebound after sharp shocks, while others cross thresholds and reorganize. Ocean chemistry tends to relax slowly as rock weathering draws down added carbon. Ecological communities can recover in form while changing in composition underneath. Reading these reactions teaches us how lasting any industrial pulse would appear to distant readers. Recovery has tempos we can measure. If a lost society once altered the carbon cycle, the sediments would remember the order of effects. Air would change first, then surface waters, then the deep ocean as mixing carried the signal downward. Land plants and soils would adjust in different rhythms than marine plankton. River fluxes would spike as storms and land use shifted erosion. The choreography matters because it can be tested across multiple independent archives. Order in time is a powerful sign. Maps of expected signal strength can focus where to drill next. Model outputs suggest stronger residues in enclosed seas and downwind shelves. Dust paths steer metals across basins, and currents sort grains by size and source. With these guides, we can design transects that test both coastal and open ocean settings. The plan looks careful on paper, then answers only to what the cores actually show. Prediction tested by core is progress. A null finding remains valuable when it is precise. It narrows possibilities and refines how we estimate background variation. It can reveal small biases in instruments or gaps in how we read a proxy. It leaves behind calibrated methods that help with other questions about ancient climate. In that sense, the search pays its way, even without a decisive discovery. Clarity loves careful bounds. Uncertainty does not need drama. It needs patience, replication, and open records that others can check. Teams that share cores and raw data invite correction and improvement. Over time, separate groups converge on what the rocks and ice actually say. That slow agreement is the deepest kind of progress in this field. Consensus formed slowly is strong. The thought experiment finally returns to the present. We can now see which of our own actions are most likely to persist in stone. We can choose which byproducts to reduce if we wish to limit our long tail. We can also design materials that either fade quickly or mark a clear timestamp. Knowing how the archive works gives us choices about the message we leave. Awareness turns into agency, not fear. The frame is now set with methods, cautions, and a map of likely places. The next step is to read the strongest candidates with care and fairness. We begin with carbon, because fire leaves a distinct chemical trail. We then weigh metals and synthetic residues against that baseline. With those lines drawn, the careful reading can start in earnest. Before we dig deeper, we must first understand the traces that time refuses to erase. We begin by naming the traces that time refuses to erase. First come carbon signals that shift when buried fuels burn at scale. Next are temperature and acidity clues preserved in shells and minerals that grow in water. Then we have metals moved and concentrated by industry, and synthetic residues that nature rarely assembles on its own. Finally, we listen for short-lived energy fingerprints and the living response recorded by pollen, plankton, and bones. Each trace is modest alone, yet together they can form a readable pattern. Carbon is the backbone of this checklist because combustion leaves a specific chemical tilt. In simple terms, the ratio of carbon-13 to carbon-12 in air and ocean tends to fall when large amounts of ancient carbon enter quickly. That drop can ripple into the chemistry of sediments as organisms build shells and as minerals lock in the surrounding balance. The shape of the curve matters as much as the size of the swing. A quick fall followed by a slow recovery points to a rapid forcing met by slow planetary buffers. If this is true, it changes how we see our place in history. Temperature comes next, tracked by tiny shifts in oxygen within shells and by minerals that favor warm or cool water. Warmer oceans hold less dissolved gas and mix differently, which changes how nutrients flow and where life blooms. On land, clay families and soil salts rearrange with heat and rain belts, leaving a mineral memory of climate. We do not need perfect precision to learn from these patterns. We need consistency across distant sites. When heat and carbon move together in time, the story gathers weight. Ocean acidity is a quiet partner to temperature, yet it leaves strong hints in carbonate minerals. When more carbon enters surface waters, acidity rises, and certain shells thin or even dissolve in sensitive zones. Deeper down, the level where carbonates start to vanish can shift upward, marking a planet-wide change in chemistry. Over years to centuries, weathering on land slowly nudges the system back, and that return arc is part of the signature. Soot and ash tell us about fire, and their microscopic shapes can separate natural wildfires from broader burning. Forests burn often enough to sketch a local rhythm, while industrial burning paints a different, more uniform dusting. Certain complex organic fragments survive better in cool, low-oxygen mud and can flag unusual combustion at scale. These are fragile hints, but when they align with the carbon and temperature story, they help close gaps. Small wins add up here, and that is the point. Trace metals provide another angle, because human activity moves them from rock to air and water in short bursts. Lead and copper rise near smelting centers and river mouths, while chromium, or nickel, can ride natural dust from specific terrains. Ratios between families of elements matter more than any single spike because ore bodies and industrial blends differ from average crust. If many coastlines show the same step in ratios during the same narrow window, we take notice. The metal story is less dramatic than ruins, yet it travels farther and lasts longer. Synthetic residues belong on the list because design leaves patterns that biology seldom replicates. Stubborn fluorinated fragments can bind to clays and organic matter, surviving transport and slow alteration. Certain pigments and additives share structures that, even when weathered, still look odd compared with natural compounds. We expect these residues to be tiny and scattered, yet a shared suite across far basins would be hard to ignore. It sounds like science fiction, but it is not starship lore. It is careful stratigraphy. Energy systems can leave subtler records that do not depend on surviving devices. Some engineered processes alter the balance of nearby isotopes in a way that marks a brief, global moment. Over deep time, the original isotopes may fade, but the altered ratios in certain minerals can persist. If a thin worldwide layer shows that fingerprint in concert with other signals, the case strengthens without leaning on lost machines. The point is evidence first, stories later. Living things respond quickly to climate and chemistry, and their reactions become part of the archive. In the sea, different tiny shell builders wax and wane as waters warm or acidify, shifting which species dominate in each layer. On land, pollen mixes tell of forests moving, grasslands expanding, or wetlands drying and refilling. Bones and teeth shrink or grow as food webs adjust, especially during rapid stress. When biology turns a corner at the same time as chemistry, we have a crossroads worth pausing over. None of these traces can stand on authority alone, so timekeeping matters. Volcanic ash beds form thin, bright lines that can be matched across continents and serve as sharp stamps in the record. Changes in the magnetic mood of minerals repeat in a known sequence and offer a broader grid of reference. Where neither is present, steady accumulation rates checked against local markers can still anchor the story. Several independent clocks are better than one, especially when the conversation spans many thousands of years. We also need a disciplined habit of comparison with natural engines. Large eruptions release carbon and dust, but they often leave thick ash and distinct mineral suites that do not mimic industry. Seafloor methane bursts can push carbon ratios quickly, yet they lack the companion package of synthetic residues and broad metal steps. Asteroid strikes leave shocked minerals and rare metal patterns that vanish in most industrial scenarios. Practicing these comparisons first keeps us honest when a tempting bundle appears. Doubt, handled well, is a form of care. Rates bring much of the insight. A planetary system pushed suddenly tends to respond with fast surface changes and slower deep adjustments. Air shifts first, then surface waters, then the deep ocean as mixing carries the signal downward in a predictable rhythm. Land plants and soils adjust to new rain and temperature patterns on their own clocks. Mapping this choreography across archives is better than debating one proxy in isolation. Field work follows from these expectations. Coastal shelves downwind of large land masses capture river cargo and street dust, making them prime for early signal detection. Quiet basins with low oxygen preserve delicate layers where small chemical differences do not get blurred by burrowing. Inland lakes with winter ice can build seasonal banding that helps test short intervals against longer ocean records. When many places whisper the same change, confidence rises. If this pattern holds, the quiet becomes compelling. Labor practice is part of the story, because modern contamination can trick us. Teams core with clean gear, cut sample interiors away from exposed surfaces, and run blanks to watch for stray molecules. Key tests are repeated in independent labs so that methods, not wishful thinking, carry the result. Shared data sets allow others to challenge the fit and refine the picture. Clean work earns clean answers. Models help set thresholds for what would survive at all. We ask how much fossil carbon burned over how many years would leave a detectable carbon-13 tilt after deep burial. We ask what mass of persistent residues would need to reach the sea for fragments to remain in low-oxygen mud. We test how strong a metal step must be to stand above natural swings carried by dust and rivers. These thresholds steer drilling and prevent overreading noise as signal. Models set the stage, and rocks decide. With the checklist clear, we can outline what a convincing bundle would look like. First, a rapid carbon tilt linked to warming and a brief rise in ocean acidity. Second, a coordinated shift in plankton and pollen that matches the timing of the chemical move. Third, a step in trace metal ratios at coastlines that echoes as a thin global veil. Fourth, a modest suite of synthetic residues repeating across distant basins in the same narrow slice. One strong line is interesting. 4 aligned lines are difficult to dismiss. Natural lookalikes must then be rehearsed as countercases. A massive volcanic episode could supply carbon and metals, yet it would also lay distinctive ashes and mineral mixes that betray its source. A sudden methane release can drive warming and acidity, but it will not produce engineered residue suites. A large impact can scramble chemistry and life, yet it leaves shock markers and rare metals that are hard to miss. Walking through these countercases before making claims is part of the craft. Now we can return to the original question with steadier footing. The search is not for cities entombed in stone, but for a thin chemical cord that rings around the world. That cord would not shout. It would hum beneath the louder music of volcanoes and impacts. If it exists, it will sit in 1 or 2 quiet layers, the kind that drilling ships pass without notice unless someone asks the right question. Maybe we have been asking that question only in recent years. Now we can ask it well. The reward for such careful work is not only a yes or a no. It is a clearer understanding of how a technological age appears to geology, including our own. It tells us which actions echo far into the future and which fade quickly into local dust. It also reveals the pace at which the planet answers sudden change with its own counterbalances. Even a null result reshapes how we read Earth. We have a path, a set of measures, and a way to weigh them without drama. The next step is to test the strongest candidates against this checklist and to see which patterns stand. If the bundle appears even faintly and repeats across distance, we will have something new to think about. If it does not, we gain confidence in the resilience and forgetfulness of stone. Either way, the reading is worth the patience. Careful measurement sits at the center of this reading. Analysts report carbon ratios relative to an agreed reference so that cores from many seas can be compared. The exact number matters less than the shared step up or down across distance. We look for the same bend in the line to appear in basins that never touched in life. Shared motion across space is stronger than a single dramatic spike. Oxygen within shells carries a temperature memory that forms when a creature grows. Warmer water shifts that balance in a steady way that has been checked in modern seas. Tiny shells called forams are common and carry this story in wide belts from tropics to poles. When many species and sizes all lean the same way, the case for broad warming grows. The method is simple in spirit even when the lab work is slow. Another useful thread comes from boron within the carbonates that make up shells. The ratio of boron 11 to boron 10 moves with acidity in surface waters. That ratio holds through burial and can be read far later with careful instruments. A rise in acidity that matches a carbon tilt and a warmth shift is not easy for nature to fake without a rapid carbon pulse. 3 chords in harmony make a stronger tone than one. Organic markers tell stories too. Long chains built by plankton and bacteria change shape with water temperature and light. Some of those chains survive burial and can be matched across wide regions. Their signals do not stand alone, yet they add nuance to the broad picture drawn by minerals and shells. It is one more place where modest hints add up to meaning. Reading soot and ash requires patience because fire has many faces. Natural wildfire produces particles with certain shapes and sizes, while broad fossil burning drifts a more uniform haze. The mix of tiny globes and broken shards can point to source when seen through a microscope. When that mix appears at the same age across distant shelves, curiosity pays off. If this pattern holds, the quiet becomes compelling. Synthetic fragments enter the record in tiny amounts and scatter widely. The goal is not to find a bottle cap in rock, but to catch a family of stubborn fragments that only design tends to make. A network of labs can agree on a short list of target molecules that survive alteration and travel. The work is delicate, yet a repeating suite across oceans would be hard to dismiss. Evidence first, stories later. Metals move with dust and water in patterns that are both natural and human-shaped. We do not ask for metal to appear. We ask for ratios to change in ways that match concentrated mining and smelting. Lead lines can nudge upward, while copper and zinc follow at different strengths, and that blend can repeat along coasts. Far from shore, the blend thins and smooths into a fine veil that still keeps the fingerprint. A shared blend at a shared time earns attention. Time control remains the constant challenge. Thin ash beds are precious because they can be matched from one margin of an ocean to another. Changes in magnetic minerals repeat in a known order and help set a scaffold. Local clocks can be drawn from growth bands in shells and layered lake mud that freezes each winter. When 2 or 3 clocks agree, the chain of cause and effect is easier to test. Resolution matters because short pulses can blur into the background if layers are mixed. Calm basins with low oxygen tend to keep layers sharp, while lively shelves can smear signals through burrowing. Researchers choose sites with this in mind and accept that some places cannot answer fine questions. Honest limits are part of sound reading. Maybe we have been asking the wrong question all along. It is not whether a site is perfect, but whether a network is strong. Let us imagine a simple walk through a core that holds a candidate pulse. The first hint is a modest fall in carbon-13 that rises back slowly, rather than snapping to normal. Within the same thin slice, oxygen within shells tells of warmer surface waters. A handful of boron readings suggest a short rise in acidity, and then a slow return toward balance. Mixed through the mud are tiny soot shapes that look more uniform than the usual wildfire story. A little deeper in that same slice, trace metal ratios step upward near a river mouth sample and appear as a faint echo in the open sea. A few stubborn synthetic fragments sit above detection in cold, quiet mud and reappear across a distant basin. The ash grid anchors the age to a narrow window that repeats in both seas. Local clocks from a nearby lake tighten the estimate without breaking alignment. 4 lines begin to hum together. Now the countercases go to work. A large volcanic episode could push carbon and metals, yet the expected heavy ash and mineral mix are missing. A sudden methane release could mimic the carbon and heat, yet it would not bring the same synthetic fragment suite. An impact would leave shocked minerals and rare metals that are not observed in this slice. Each natural path explains part of the bundle, not the whole. If this holds, the map becomes a compass. Statistical care keeps such a reading from racing ahead. Analysts pre-register the comparisons to avoid chasing noise. They set thresholds for what counts as a shared signal across distance and what counts as a coincidence. Independent teams test the same sections with fresh instruments and their own workflows. Agreement reached slowly is the most durable kind. Field design benefits from maps drawn before a single ship leaves port. Atmospheric models show where dust and smoke would have drifted during the suspected window. Ocean models show where currents would have carried fine particles and where they would have settled. These maps suggest transects from tight coastlines to open waters that best test the idea. Planning shapes the odds, but rocks have the last word. Coastal cities cluster near river mouths, so these shelves are the likeliest places for early signal, yet coastlines move with rising seas and sinking deltas, which is why drowned valleys and ancient estuaries matter. Sediments there often stack quickly and preserve short pulses as clear lines. Offshore, deeper basins filter the noise of storms and tides and keep annual layers flatter. Together, these places balance detail and persistence. Cold seeps and oxygen-poor basins are allies in this work. In such places, scavengers are rare, burrowing is slow, and delicate chemical differences remain crisp. Even small fluxes of synthetic fragments or fine soot can settle and stay put. These settings do not tell every part of the story, but they keep the script legible across long spans. Legibility is the quiet hero of this search. On land, peat and lake beds add contrast and human scale. Pollen counts reveal forests shifting north and south with changing belts of rain and heat. Lake varves stack year by year and can show whether a pulse was sudden or drawn out. River terrace gravels fix moments when flows surged and waned during wider climate swings. Land and sea together show how far a driver reached. Some readers may wonder about direct artifacts sealed in unusual places. Salt domes, tar pits, and dry caves can preserve fragile matter for long spans, yet they are local and rare. Their finds would be evocative, but not global. The broad case rests on signals that traveled and settled across half a world. That is why chemistry and ratios carry more weight than any single object. Energy systems are abstract, but their shadows are practical. Short-lived isotopes vanish quickly, yet the shifts they trigger in nearby elements can freeze into minerals. Even a brief global sneeze of altered balance can form a thin line that later labs can read. If that line sits with the carbon tilt and the warmth, it joins the bundle as a quiet vote. Quiet votes add up. The craft also includes restraint and language. We use words like suggests, consistent with, and unlikely to, instead of declares and proves. We describe the strength of fits and the size of gaps in plain terms. Precision builds trust when it avoids drama. Calm sentences help listeners hold complex ideas. Error bars deserve airtime because deep-time reading is never exact. Instruments have limits, and burial changes even stubborn matter in slow and uneven ways. Teams publish ranges, not single sacred values, and they stick to what the data can carry. Honesty about limits is not weakness. It is why the work remains useful years later. Bias is a known guest at any table and must be managed. Groups that want to find a signal will tend to see one unless they set rules in advance. That is why blind interlab comparisons and repeat coring at fresh sites are built into the plan. Disappointment is allowed when a hint fades. Relief is allowed when a tidy story fails a fair test. Communication with the wider public can also help. Maps, simple timelines, and clean statements of what was searched and what was found invite participation. When people understand the rules of the test, they can follow progress without needing each instrument detail. Shared understanding reduces the noise that often surrounds big ideas. It keeps the focus on what rocks and ice actually say. There is a secondary reward hidden in this method. By learning how an industrial pulse would look after long burial, we learn which of our current practices will linger. We can choose to reduce the most persistent fragments, or to tag our own time with clear but harmless tracers. That decision would be a gift to future readers who face their own puzzles. Choice is a form of care. Case studies from natural history help train the eye. Past warming events show how fast oceans can acidify and how long they take to relax. Ocean anoxic intervals show how life responds when water turns still and breathless. Sudden impacts show how sharply chemistry and fossils can jump and then settle. Each case writes a template we can hold against new cores. Even with strong preparation, many candidate sites will yield only partial hints. A clean carbon tilt without the metal step may point to natural causes. A metal step without warmth may point to dust storms and shifting winds. Single hints are not useless. They help refine the maps and the questions. Over time, the network of sites sharpens the picture. Some of the most helpful progress comes from negatives. When a predicted bundle fails to appear in a likely basin, the idea narrows and becomes testable elsewhere. Teams publish these misses alongside hits to prevent duplication of effort. Clear misses are as valuable as clear finds because they harden the method. The search improves even when the answer is not there. Ethics enters quietly through patience and credit. Ship time and core samples are precious, and many hands lift the work. Teams make room for new readers and share data with rivals who can test their claims. This culture slows the news cycle and raises the signal to noise ratio. the result is knowledge that lasts. In the lab, sample prep is as important as the instrument. A sliver cut from the quiet center of a core will speak more cleanly than a piece that touched air. Rinses and blanks watch for ghost molecules that can drift in from modern life. Every step is written down so another lab can walk the same road. Repeated paths build trust. When a promising bundle appears, the most conservative path is to try to break it. Teams search nearby layers for natural lookalikes that could fool the eye. They attempt to reproduce the suite with mixtures from known volcanic or dust sources. If those attempts fail, the claim gains weight without ever using grand language. Strong claims are quiet claims. In this work, patience is not just a virtue, it is a tool. Rocks keep their own pace, and our duty is to match it. Care taken now prevents confusion later, when new cores appear from other seas. The archive is slow, but it is generous to careful readers. If we move slowly, it speaks clearly. We return to the map that began this plan. Coastal shelves, drowned valleys, quiet basins, and frozen lakes stand ready to answer. The tools are in place, and the rules of reading are clear. What remains is to listen for a chord that rises above ordinary music. If that chord is there, we will hear it. We turn now to the first candidate signals and ask them to speak plainly, one line at a time. We start with the carbon tilt because it is the clearest candidate for a global pulse. The idea is simple enough to test. Look for a rapid fall in carbon-13 relative to carbon-12 that recovers slowly, and check whether warmth and acidity move in step. Sharp changes that align across distant seas are better than dramatic spikes in one place. If this pattern exists within a thin slice that can be dated well, it earns our attention without any grand claims. Cores from quiet basins tend to show the cleanest curves. In these places, burrowing is limited, oxygen is low, and the layers keep annual or near-annual structure. A thin dark band that matches in two distant cores, each with its own clocks, is a strong start. We would then ask whether small shells from the same interval show lighter oxygen that points to warmer surface waters. If those shells record warmth while the carbon tilts, the two lines of evidence begin to harmonize. The return toward balance matters as much as the drop itself. Oceans and rocks take time to pull added carbon back out of the air, and that slow drift becomes part of the signature. A curve that falls quickly and then rises over centuries to millennia tells of a sudden push met by slow buffers. If the fall is gentle and the rise is flat, the driver may be different. Shape over time is a better guide than the size of a single jump. Next, we would test for soot and complex organic fragments that point to broad burning. Natural wildfire leaves a local rhythm. A more uniform haze across far basins suggests something else. Under the microscope, tiny spheres and ragged shards carry different stories about heat and source. If those shapes drift together with the carbon tilt and warmth, curiosity gets a nudge. Evidence accumulates when small details agree. Boron in shells joins the check by speaking for acidity. A brief rise in acidity should track the carbon entry into the surface ocean, before deeper waters catch up. That rise would thin certain shells and shift the depth where carbonates vanish in the deep. If a change in that depth appears around the same time in distant oceans, the case for a rapid forcing grows. We are not hunting for perfection, only for a bundle of signs that move together. Trace metal ratios on nearby shelves can round out the picture. Near river mouths, we might find steps in lead, copper, or zinc that arrive slightly before the thin, global veil offshore. This lag makes sense because coasts feel the pulse first, while the open ocean collects a blended signal later. A shelf step paired with a faint offshore echo suggests a driver that began on land and spread through air and water. Timing that fits a simple map is a quiet reward. Now to the fragile family of synthetic residues. Targets would include altered fragments of sturdy fluorinated compounds and a short list of pigments or additives that do not readily form in nature. These are needle-in-haystack finds. So the test is not a single detection, but a repeating suite in 2 or more distant basins. Even a small, consistent package would be worth a closer look if it sits in the same thin slice as the carbon tilt and warmth. This, again, is about bundles and timing, not trophies. Biology ought to respond as well, though not always in predictable ways. In the sea, small shell builders may swap dominance in bands that match the chemical moves. On land, pollen mixes may show plant communities shifting as rain belts move and heat builds. Short, stressful intervals can shrink animal bodies or alter tooth chemistry as food webs adjust. These are local echoes, but when many echo at once, they point to a shared driver. Every claim leans on clocks. Ash layers lock a day, a week, or a season into a bright line that can be matched across continents. Magnetic mineral flips add broader stamps that repeat in a known order. Where both are missing, steady layers in lakes or quiet seas can still be counted and compared to regional events. 2 or 3 clocks tell a steadier story than one. We have to test counter cases with the same energy. Volcanism can push carbon and metals, but it tends to leave thick ash and distinct mineral fingerprints. Methane from the seafloor can drive a sharp carbon move and warming, but it would not bring engineered residue suites. A large impact can do many things at once, yet it also leaves shocked minerals and unusual metals that betray its cause. Practicing these comparisons first keeps the language careful and the claims modest. Suppose a candidate bundle appears: a swift carbon tilt, warmth, a thin acidity rise, a shelf metal step with an offshore echo, and a faint suite of synthetic residues. The next step is not announcement, but replication. Independent teams would test parallel cores, repeat extractions, and share raw data as they fail to break the bundle. If the suite stands, it grows heavier without anyone raising their voice. There is a philosophical payoff to this patience. By building a method that would detect an old industrial age, we also learn how our own age will read after long burial. We discover which of our habits carve deep grooves and which wash away within a short span. This knowledge offers choices about materials, energy, and waste that will shape the far future of our thin layer. Agency grows from understanding, not from fear. Now consider how geography shapes expectations. Dust trajectories carry metals across oceans in arcs that repeat with winds and seasons. Currents sort particles by size and steer them into basins, leaving thick records in some places and thin ones in others. Shelves near big rivers trap more land signals. Far gyres blend them into a global average. These patterns tell us where a faint signal has the best chance to survive and be seen. Coring campaigns build on these maps. A typical line might begin on a drowned river valley, step offshore to a quiet slope, then reach into a deep basin with low oxygen. Each site offers a different filter and timescale, and together they assemble a more complete story. When the same thin slice winks at us from each stop, we know we are not chasing a local quirk. Repetition across distance is a mark of real change. The work continues on land as well. Lakes with clear seasonal layers can catch the early moments of a pulse, showing whether change came as a shock or as a ramp. Peat preserves airborne particles and organic hints that help separate regional fires from broader burning. Cave minerals grow slowly and record shifts in rainfall that can align with the ocean story. Land and sea in concert make for clearer music. Throughout, communication matters. Simple figures that pair time on one axis with 2 or 3 clean curves help more than complex composites. The point is not to impress, but to make the logic visible. When people can see each curve and the way they stack, the bundle stops feeling mystical. Clarity invites trust. There will be frustrations. Some cores will be disturbed, some instruments will drift, and some promising hints will fade with better controls. Publishing those disappointments is as important as sharing the hits because it prevents others from walking the same dead ends. Knowledge grows when maps include the cliffs as well as the roads. Honesty keeps the noise down. The prize, if it comes, will not be a headline, but a careful diagram. A thin band on multiple cores, a set of gentle curves rising and falling in step, a handful of ratios marching together. Add a table of small, stubborn residues repeating in the same slice across distance. That is the shape of a quiet discovery that would change how we see our place in time. There is a family of nitrogen clues that deserve a place in the bundle. When oceans warm and mix less, low oxygen zones can stretch and alter how nitrogen moves through life. The balance between light and heavy nitrogen in organic matter can shift in ways that track this stress. Buried layers then keep that balance long after the plankton are gone. If nitrogen leans at the same time as carbon and warmth, the chorus gains another careful voice. Sulfur can join the story through the quiet work of microbes. In waters that turn still and low in oxygen, bacteria change sulfur in ways that leave distinct mineral forms. The ratio of sulfur 34 to sulfur 32 can drift during these spells. Those minerals then sit inside the rock like tiny logbooks. When sulfur and nitrogen tell a shared tale with carbon and boron, patience begins to feel rewarded. Calcium and magnesium in shells also respond to temperature and chemistry in steady ways. The ratio between them can shift as waters warm or cool across seasons and longer swings. Individual creatures record local conditions, yet large counts reveal broad moves. We do not need perfection from each shell when the group speaks with a single lean. Groups smooth the noise without hiding the signal. Magnetic grains add a practical cross-check that is easy to miss. As sediments settle, tiny magnetic particles align with the field at that time. Over very long spans, the field flips, and those flips appear as a staircase of directions in the rock. Matching that staircase between cores helps tie distant stories together. A shared staircase is a gift when other clocks run thin. Grain size and sorting teach us about energy in the water above the site. Calmer waters drop finer grains in even sheets, while storms and currents lay thicker, mixed beds. A sudden run of fine, even layers can signal a shift to quieter conditions that match a broader change. The texture of the mud becomes a plain hint anyone can see. Texture guides the eye before chemistry supplies the details. Even the color of a layer can be a first whisper. Dark bands often hold more organic matter and can align with times when the sea turns still and breathless. Light bands may mark times with more minerals washed from land. These simple cues avoid overreach and help choose where to cut thin sections for closer tests. Simple guides save time and reduce wishful thinking. Bioturbation, the stirring by small animals, can blur signals, yet the blur has a pattern. Where burrows are common, layered lines soften and microstructures break. Where burrows are rare, fragile laminations stay crisp like pages that were never thumbed. Reading the degree of blur tells us how much to trust a delicate chemical record. Trust grows where pages stay crisp. Cave minerals on land, called speleothems, offer clean water stories. Drop by drop, they trap the balance of oxygen and carbon that flowed through soil and stone. Shifts in these balances can track rainbelts that move with heat and ocean patterns. When cave records tilt in step with ocean cores, land joins the sea in a single, slow voice. Two worlds speaking together are hard to ignore. Tree rings, for the spans they cover, add focus to the start of a move. Wide rings mark good years, and narrow rings tell of stress like heat or drought. Chemistry within the wood can hold a trace of air and rain at the time of growth. While trees do not speak across millions of years, they can anchor the opening chapter of a story in younger archives. Anchors near the start help date the rest. To keep language honest, we treat every proxy as a witness with limits. Carbon ratios lean with many causes, and so do shells and grains. A witness is most helpful when others tell the same timeline with their own accents. The job is to ask several simple questions and compare the answers. Agreement, not eloquence, sets confidence. Instrument drift is a quiet foe that we plan for in advance. Labs run standards with known values before and after samples to catch slow changes. Teams swap blind samples to see whether numbers match across different benches. When the same thin slice speaks the same way in different rooms, confidence rises a little more. Quiet checks make strong claims possible without loud words. Storage and handling can change delicate material in sneaky ways. Heat, light, or oxygen can alter organic hints before they reach the instrument. That is why cores are capped, sealed, and kept cold until cutting and testing. Notes track every handoff so sources of trouble can be traced and ruled out. A clean chain of custody is a science in its own right. Let us imagine a second core from far away that seems to match the first. The carbon tilt appears at the same relative depth once the clocks are aligned. Shells lean to warmer waters, and the boron story nods toward a brief rise in acidity. Metals on the nearby shelf show a small step that fits the map, and a few stubborn residues repeat. This is not proof. This is an invitation to look harder. We then sample above and below to define the edges of the slice. If the bundle fades cleanly outside the thin band, the case for a short event grows. If hints smudge into the layers above and below, mixing may be to blame. Edges that are sharp across distance are better than edges blurred by local stirring. Sharp edges argue for a real moment rather than a long drift. A third line in a new basin becomes the turning point. Oceans differ in how they breathe and in how they carry dust and river cargo. If the same thin band appears in a basin with different habits, the driver was likely global. Diversity of settings protects against a local story being read as a world story. Diversity makes the bundle sturdier. There is room here for a gentle nod to familiar tales. It may sound like a detective plot, but the detective is patient geology. The clues are not car chases, but curves that lean together. The reveal is a quiet page that reads the same in far libraries. If this is true, it changes how we hold our own chapter. The next stage is to ask whether the bundle belongs to a known natural driver. We compare to catalogs of eruptions, impacts, and methane bursts, already mapped in many cores. Where dates overlap, we test for the special fingerprints of those drivers. If a fit is clean, we accept it and move on. If the fit fails on key marks, the candidate remains on the table. Communication of uncertainty is part of the craft. We use words that match the weight of the evidence, and we keep claims proportional. People can handle uncertainty when the path is clear and the rules are simple. A fair frame builds patience outside the lab as well as inside. Patience is the hidden engine of this entire search. Education efforts turn complex proxies into plain images. A line for carbon, a line for warmth, a line for acidity, and a bar for metals can sit on a single page. Dots mark the thin band in each core and make the alignment visible without jargon. Once the logic is visible, the mystery feels smaller and the wonder feels earned. Clarity scales curiosity. Some have asked whether technology today could plant a deliberate signal for future readers. The answer is yes, though care is needed to avoid harm. Harmless tracers with distinct isotopic balances could mark a short interval without lasting damage. Records of where such tracers were set could live in many libraries for redundancy. This idea is not a stunt. It is a way to practice humility across time. Ethical reflection does not slow the science, it guides it. We avoid dramatic claims because they age poorly when data grow. We share methods so rivals can test and refine our steps. We honor patience because speed often confuses the very signals we hope to read. Calm work makes sturdy bridges for others to cross. It helps to rehearse how a false positive would be handled. Suppose a slice looks right in two places, but fails in a third. The plan calls for more cores along the path that winds connect and currents follow. If the slice vanishes along that path, the hint was local. The map closes one door and points us to another. Conversely, we should rehearse how a true bundle would mature. First comes the diagram that shows the aligned lines in several places. Next comes a set of tests that try to mimic the bundle with natural mixtures and fail. After that, the community checks the clocks and the chemistry in new labs. Only then does the idea graduate from hint to candidate. Even then, the language stays measured. At some point, the search becomes routine rather than speculative. Students learn to read the curves the way meteorologists read pressure maps. They argue over small angles and subtle lags, rather than over broad claims. Progress feels quiet from outside, but inside, it feels like a craft reaching maturity. Quiet crafts change how we see. There is a soft human reward woven through all this. Taking the long view breaks the spell that places us at the center. We become one layer among many, with duties to those who will read us later. That feeling is not fear, it is perspective. Perspective is its own kind of awe. When the thin band is finally mapped across basins, its thickness and strength will vary. That variation is not a flaw. It is a map of how the world breathed during the pulse. Coasts will speak loudly, and open oceans softly. Lakes will whisper of seasons and storms that the seas smooth away. Together they make a choir rather than a solo. The last check is always the simplest question. Does the bundle make more sense as a natural event that we already understand? Or does it ask us to consider an industrial driver without leaping to grand stories? If the second path remains after fair tests, the idea earns a seat at the table. Earning a seat is enough for now. Age models, the timelines that match depth to time, decide whether distant stories can speak together. A good age model uses several anchors, like ash beds and magnetic flips, then smooths between them with rates that fit the local record. We test how sensitive the model is by nudging these rates and checking whether the bundle survives. If small nudges erase the alignment, the claim is fragile. If the bundle holds, confidence grows. Robust timing is quiet strength. When many curves sit on the same page, we can ask whether a hidden pattern ties them together. A simple tool for this is to find the dominant shared motion, the part of the changes that most curves agree on. If that shared motion peaks where the thin band sits, it supports the idea of a single short driver. If each curve wanders on its own path, the case weakens. Agreement is a form of signal, disagreement a clue to look again. After we fit a simple picture, we study the leftovers. Leftovers, called residuals, are what remains after the expected pattern is removed. If those leftovers look like noise, the fit is clean. If they carry structure, something real is missing from the story. Residuals guide the next round of sampling because they point to gaps. The map improves one small correction at a time. Provenance, the story of where sediments come from, adds geographic sense to the bundle. Minerals and tiny rock fragments carry fingerprints of the lands they left. When a coastline layer shows more material from a mined region during the same window as the chemical tilt, the lines cross-check. Far offshore, the same fingerprint fades, but remains detectable. Source and timing together quiet the doubt. Clay families respond to climate and supply. In wetter times, clays that swell can increase, while in drier times, other clays dominate. These shifts are plain under a microscope and track with changes in rivers and winds. When the clay story bends in step with carbon and warmth, we gain another modest line. Modesty is not a weakness when many modest lines agree. Microscopic shells change form when waters change, and form is a fast messenger. Some species build lighter or thinner walls under stress. and some retreat while hardier cousins spread. We count species, measure sizes, and compare shapes through the thin band. A calm cadence of change in these tiny builders that matches the chemistry is hard to dismiss. Life leaves patterns that are quick to read once you know where to look. Phosphorus rides with life and tells us about productivity in the water. A brief surge in nutrients can bloom and then crash, leaving subtle changes in organic remains and minerals. If the thin band holds signs of a short feast followed by a lean period, it fits the rhythm of sudden forcing. We do not need bright colors on the page, just a consistent rise and fall. Rhythm carries meaning. Taphonomy, the study of how remains turn to rock, explains why some hints fade and others persist. Soft bodies vanish first, fragile shells dissolve, and robust minerals survive to write the last word. Knowing this order prevents us from overreading what is missing. It also helps explain why chemistry often speaks when objects do not. The recorder is selective, and that selectivity can be mapped. Time averaging adds another layer of caution. Layers can blend years or decades into a single thin slice, which hides sharp starts and stops. Choosing sites with finer layers helps, but we still treat sharp lines with care. A pulse that looks slow may only look that way because the page is coarse. Reading resolution is part of reading truth. Pre-registration, a simple promise to write the test plan before seeing all the data, keeps us honest. We state which curves we expect to move together and what size of shift would count. We list the natural drivers we will test first and the thresholds that must be met. When results arrive, we follow the plan unless the data force a clear change. Plans do not bind the truth, they bind our bias. Open archives tie the work to the wider world. Core images, raw numbers, and lab notes live in shared libraries that anyone can read. Students and rivals can replot the curves and test new fits without waiting for permission. Errors surface early, when many eyes can see the same page. Openness is a speed that does not rush. Sampling design learns from first tries. If a shelf site shows a strong metal step, the next line moves along the current to see where the step thins. If a basin site holds a crisp band, the next core tests up current and down current to check the shape of the plume. Each new point is chosen to answer a small, clear question. Small questions stack into a sturdy map. Logistics matter because the best evidence is useless if it never reaches shore. Ships plan routes around storms and ice, and teams train for cold, dark work that lasts through the night. Clean rooms on board let first cuts and seals happen before modern air can touch the cores. Care taken at sea saves months of repair work on land. Many hands make the quiet band possible. Back in the lab, gentle methods protect fragile markers. Solvents are chosen to lift target residues without erasing them. Filters are baked clean, bottles are rinsed with pure water, and tools are set aside for single uses. The rigor may seem fussy, yet this fuss is the thin wall between real signal and laboratory shadow. Care is the shape of respect for small things. Visualization helps people feel the logic before they know the jargon. Curves sit on shared time axes with shaded bands for uncertainty, a word that simply means the honest range of possible values. Thin horizontal bars mark ash ties and magnetic steps so alignment is visible at a glance. Labels stay plain and brief to keep the voice calm. Clear pictures teach without shouting. Training the next readers keeps the craft alive. Students learn to prepare samples, to question early wins, and to enjoy null results that narrow the field. Field schools visit outcrops where ancient layers are on display, so the archives feel like places rather than charts. The method becomes a culture, not just a set of tools. Cultures remember what single experts can forget. There is a question about signals that start on land and never reach the sea. Some residues bond tightly to soils and may stay near riverheads for long spans. Lakes and peatlands then become the main witnesses for those fragments. That is why land records belong beside ocean records throughout this search. The world speaks in many dialects, and we need translators. We also consider how winds sort dust by size and height. Fine particles ride high and cross basins, while heavier ones drop near source. A thin global veil is usually made of the smallest travelers, so we look for their signature minerals in the quietest muds. Coarse grains point us back to shore to search for the first push. Size is a compass, simple and reliable. Sometimes a silence is the message. If a site that should have recorded a plume shows nothing, the plume may have flowed another way. That absence redraws the arrows on the map and improves the model. Silence is not failure. Silence is a path cleared of guesses. The next core follows that cleared path. The longer we work, the more the extraordinary shrinks into the ordinary work of careful reading. A possible industrial band becomes another case file on the shelf beside eruptions and impacts. The file grows with each check and each quiet confirmation, or it is closed with a note that the bundle dissolved under light. Either way, the archive is better organized for those who come next. Order is a gift. A subtle social benefit follows. When people see how claims are tested and tempered, trust grows, even when answers are slow. The story becomes a shared project rather than a contest of dramatic voices. Patience spreads beyond the lab and into how we think about change. Shared patience is a durable resource. If the bundle never appears, we still learn to read a world that keeps only what it must. We learn which signals blur, which endure, and which depend on places that are rare. That knowledge helps us design materials and policies that are kinder to the record. Kindness to the record is kindness to the future. If the bundle does appear, we'll be thin and calm. It will not shout from cliffs or glow in a museum case. It will lie in drawers, in labeled bags, and quiet plots, waiting for readers who trained themselves to listen. The surprise will be how undramatic the moment feels. The change will live in how we think afterward. Either way, the method gives us a way to hold a grand question without shaking it. We can ask about others who might have risen and vanished without losing our footing in evidence. We can accept a no with gratitude and a maybe with measured curiosity. That balance is worth carrying into other mysteries that stone can answer. Balance is its own kind of wisdom. We set down the pen for a moment and look again at the thin, dark band. It still sits there, quiet and patient, framed by ash ties, and lined with tiny shells that tell of warmer surface water. The page around it is full of ordinary life that went on before and after. The band is only a breath, yet it could hold a chapter. A breath can be enough. The quiet band is the doorway, but the room beyond holds the perspective we came for. A thin industrial cord, if it exists, would place our own layer in a humbling context. We are one chapter among many, not the book. That perspective changes how we plan, design, and speak about the future. First comes design that listens to geology. If we do not want stubborn fragments to linger, we can choose materials that turn benign under pressure, heat, and time. If we want a clear timestamp for future readers, we can choose harmless tracers that stand out without harm. In both cases, we accept that we are writing in stone, whether we mean to or not. Writing with intention is wiser than writing by accident. Second comes energy with an ear for the archive. Systems that release fewer long-lived residues will fade faster in the geological record. Systems that vent large volumes of ancient carbon will ring loudly in the thin band. We do not need slogans to understand this. The rocks will either speak softly of us, or they will not. The choice is practical and testable. Third comes the culture of measurement. Open data, careful methods, and the habit of replication make it easier for future readers to trust what we thought we saw. Archiving cores and notes in many places reduces the chance that the thin band's context is lost. These are simple habits that raise the quality of questions we can ask. Good questions echo farther than grand claims. There is also comfort in limits. The seafloor will recycle, mountains will wear down, and lakes will fill and drain. Most pages will be lost to subduction, uplift, and erosion. Knowing this does not breed despair. It breeds clarity. We work where the record is kind and accept that kindness is rare. Maps sharpen our sense of where kindness lives. Enclosed seas with low oxygen keep fine layers. Downwind shelves catch dust and river cargo. Polar lakes write annual lines that a careful hand can count. Caves and peats hold the breath of land. The list is short, but it is enough to try. Now we glance back at earlier worries about fear and fantasy. A grand question can attract theatrical answers, yet the archive rewards calm curiosity. We do not need drama to feel awe. We need scale and evidence. Scale tells us how small we are. Evidence tells us what kind of small. That is an honest kind of wonder. We should also mind our language for those who will meet this idea for the first time. Short sentences that carry one idea, then rest. Plain words that describe cause before effect. A rhythm that returns to the checklist and the map, so that people do not get lost. Clarity is an act of care for the listener. Sometimes people ask why this reading matters if the answer is a quiet no. The answer is that the method improves how we listen to Earth. It helps us separate noise from signal in every question that involves deep time. It shows us which archives are generous and which are stingy. That knowledge pays off whether or not a thin industrial band exists. There is a deeper human reason too. A long view makes room for humility without humiliation. It lets us feel small in a way that opens rather than closes. If others rose and vanished before us, we are reminded that complexity is fragile. If no others did, then our layer is uniquely responsible for what comes next. The bundle itself, if confirmed, would not answer every question. It would not tell us who lived, what they believed, or how they built. It would tell us that for a brief span, the planet wore an industrial mask that it later set down. It would tell us that chemistry remembers when monuments do not. That is enough to change the mood of our story. Our own choices then take on a different color. We can pick materials that turn to simple dust or to gentle salts rather than to stubborn ghosts. We can close loops so that metals return to use rather than to river mouths. We can measure impacts with the same humility we use to find the band. Choices write chapters, and chapters can be gentle. Education could carry this calm into classrooms. Students can touch cores, read curves, and practice building bundles from simple proxies. They can learn how to be patient with evidence and generous with null results. The lesson is not that mysteries are solved with drama, but that they are read with care. Care scales. Policy gains a tool that is both modest and strong. Instead of arguing about distant possibilities, we can ask which practices will leave the clearest scars. We can then choose to reduce those scars, or to mark our time with readable but harmless stamps. The question becomes simple. What do we want the archive to say about us? Simplicity cuts through heat. There is an art to leaving a note for the future. It should be durable, clear, and kind to the record. It should be placed in archives that tend to survive and duplicated in many places. It should be described in many languages so that readers with different tools can find it. Notes, like cores, travel better when they are light. Let us return to the band one last time and imagine the diagram on the table. Curves of carbon, warmth, and acidity bend together. A bar of metals steps up on shore and thins at sea. A short list of residues repeats in two distant basins. Tiny shells and pollen agree on a brief, stressful turn. The picture is quiet but clear. What follows from such a picture is not triumph or fear, but a change in posture. We would speak more softly about uniqueness and more clearly about stewardship. We would trade slogans for measurements and anecdotes for maps. We would accept that our page is thin and write it with care. Now the last quiet question. If the rocks remember us, what do we want them to remember? That we burned brightly and vanished, or that we learned to listen and adjust? The archive will not answer for us. It will only repeat what we did. That is both the warning and the gift. We can widen the lens and ask how design teams would act if they took the archive as a client. Materials that perform well in daily use could also be tuned to fade into harmless pieces under deep burial. Ceramics and glasses could be formulated to carry brief, clear markers that endure without harm. Durable alloys could be reserved for loops that rarely touch rivers or air. Design can serve both present function and future legibility without choosing one over the other. Architecture can think beyond the service life of walls. Foundations near shifting coasts can be planned so that retreat leaves minimal residue. Structures in river plains can be built with soils and fibers that return to local cycles under pressure and time. When removal day arrives, parts can return to loops instead of to deltas. Buildings then speak softly to the record when they are gone. Agriculture carries a large pen when it writes into the mud. Soil care that limits erosion keeps deltas from recording sudden bursts of dust and metal. Fertility guarded with precision reduces the nutrient surges that read as feasts followed by famines. Wetlands kept intact filter residues before they reach shelf muds. Fields and marshes become quiet partners with future readers. Industry can chart its own echoes. Mines that close their loops keep distinctive ore fingerprints out of distant veils. Smelters that trap fumes turn trace metals into assets rather than signatures. Water systems that capture ultrafine particles prevent stubborn fragments from drifting far. The same steps that improve present air and water also soften the thin band. Waste is a design problem dressed as a habit. When packaging returns to collection with ease, fewer fragments escape into quiet basins. When the most persistent compounds are replaced by gentler cousins, residues fade before they become part of stone. When reuse becomes the default rather than a novelty, rivers adjust their loads. Habits, not slogans, decide what the archive will keep. Education can give people the pleasure of reading rocks. A classroom can stage a small coring with layered gel that records a week of simple events. Students can add colored dust, bubbles, and shells to see how signals stack. They can cut the gel and try to reconstruct the week without notes. That practice makes the logic of proxies feel natural. Museums can anchor deep time in an afternoon. A single drawer with paired cores, one from a busy shelf and one from a quiet basin, can teach how place shapes memory. A simple panel can show carbon, warmth, and acidity curves that lean together across the same thin stripe. Hands learn faster than eyes alone when the samples can be touched. Touch lowers the wall between people and time. Storytellers can help without leaving the ground of evidence. A tale that follows a core from ship to lab and then to a shared archive has its own quiet drama. The characters are the patient tools, the cautious sentences, and the thin band that refuses to be loud. Wonder grows when process is visible and pace is honest. People trust what they can watch unfold. Policy can use the archive as a mirror for impact. When two options serve the same need, the one that leaves a lighter global residue is the wiser choice. When a practice writes a clear scar, it earns the closest scrutiny. This is not morality dressed as geology. It is geology used as a practical ruler. The ruler is slow, but it is fair. Finance can translate the slow ruler into present incentives. Insurance can price floodplains with an eye for drowned archives and lost cores. Bonds for restoration can include clauses that protect prime sites that hold long stories. Funds that value materials built for return rather than discard can win twice, now and in the record. Capital can be patient when the horizon is clear. Law can guard places that carry more than scenery. A quiet basin that keeps annual layers is a library without walls. A cave that grows dripstone pages is a climate ledger written in mineral script. A peatland that stacks plant breath is a chapter on air and rain. Protecting these places protects the patience of everyone who comes after. Language matters when we explain why protection is needed. We can say, simply, that some shelves and lakes are rare machines that measure time. We can say that once stirred, their pages cannot be put back in order. We can say that they are textbooks no one can rewrite. Plain reasons carry farther than grand speeches. On the research side, we can plan a global reading list. A handful of basins on each ocean, a ribbon of shelf sites near major rivers, a suite of lakes across latitudes, and a set of caves along storm tracks. Each would host a small, open library of cores and thin sections. The list would be short enough to maintain and broad enough to answer. A modest canon beats a mountain of forgotten notes. Technology can widen ears without changing the song. Instruments that scan thin sections without lifting a speck preserve precious slices. Robots that core in cold, dark waters extend reach without stirring the page. Algorithms that align curves can propose fits while humans judge them. Tools serve best when they keep the record calm. Digital memory must respect the slowness of the archive. Files that explain methods and place live in many libraries, with simple formats that do not fade quickly. Captions use plain words and minimal jargon so that future readers can translate. Diagrams include scales and legends drawn with restraint. The goal is not flash, but survival. There is also room for art that does not pretend to be data. A sculpture that stacks layers of glass with faint pigments can teach how thin bands carry meaning. A poem that counts years in breaths can nudge people to feel time. These are companions, not evidence, yet they often open the door for evidence to be heard. Feeling can prepare a mind for patient thought. In families and communities, the archive idea becomes a quiet habit. People notice the river after storms and wonder which grains will travel far. They watch news of fires and think about soot crossing basins. They see a core on a screen and understand why a thin band matters. Curiosity spreads without needing a banner. We should speak about hope in a plain way. Hope is not a promise that a signal will or will not appear. Hope is a choice to keep reading and to keep sharing what the pages say. It is the belief that careful work changes minds, even when it changes no laws. Hope is a discipline that looks like routine. There is a temptation to make the mystery larger than the evidence. We can decline that temptation and still keep the wonder alive. The scale of Earth and the strangeness of time are already vast. The quiet band, if it exists, is already an astonishing idea without decoration. Decoration would only blur the edges of a clear shape. If the band never appears, nothing is lost. We will have learned how to listen better and how to teach others to listen. We will have protected a few more pages from being torn before they are read. We will have drawn a map of where knowledge survives best. That is a fine harvest for a careful search. If the band appears, much is gained, yet little changes overnight. No city rises from the mud, no names return, no voices speak. What changes is our angle of regard. We see our own layer as one among many, and adjust our tone. That tone guides choices long after headlines fade. Take a breath and imagine the far future reader. They cut a thin slice from a quiet core and set it under light. They trace a gentle fall in carbon and a soft lift in warmth, then a return. They see tiny shapes of soot and a whisper of odd residues. They close their notes and sit for a moment with the feeling. What would we want that reader to think? Perhaps that we learn to ask careful questions about those who may have come before. Perhaps that we chose materials and habits with an ear for the long echo. Perhaps that we left a brief, clear mark that did not scar the page. Perhaps that we listened. At the end, humility is not an apology, but a stance. The stance says that evidence leads and stories follow. It says that small signals, repeated and aligned, can carry large meaning. It says that quiet work can sustain awe without noise. That stance is strong enough to hold a mystery for a lifetime. So we come back, full circle, to a sentence we can keep. Rocks remember patterns more than monuments. The quiet band is a pattern we can test with patience and care. Whether it speaks of us alone or of others too, the method remains the same. Read slowly, compare gently, share openly. If we adopt that method, our brief layer becomes a gift rather than a riddle. We give those who come after a clean path to understand what happened here. We give ourselves a calmer way to act in a world that keeps only some stories. We set pace by stone rather than by rumor. Pace by stone is kind to minds. One last look at the imagined diagram on the table. Curves gather, edges align, and the thin band holds its measured arc. Beside it sits the map of sites, the list of methods, and the notes on what did not work. The picture is not a shout, but a steady hand. A steady hand can steer through deep time. We close the folder and place it among other careful files. The room is quiet. Outside, rivers and winds continue their slow riding. Somewhere, a drill lowers through water toward another page. The archive continues, and so does the patient joy of reading it.